Alright, today we're talking about properties on the nanoscale. So first, in a nutshell, we mentioned this in class already. If we're talking about classical physics, we're talking about physics at the macro scale. So what happens to things that we can see? Quantum physics is the physics at the micro scale, so things we can't see. And it's a whole different world. So in classical physics, where matter and energy are two separate concepts, you'll recognize, if you've taken physics, some of these different topics. Mechanics, dynamics, hydrodynamics, statics, optics, thermodynamics, acoustics, magnetism, electricity, and more. Quantum physics talks about energy in a way where they come in little packets called quanta. So their energy is not continuous, but they're found in these discrete packets. There are 5 main ideas in quantum theory. The first is what I was just talking about. Energy is not continuous, but it comes in these small, very defined packets. What's interesting about particles, such as electrons, they behave both like particles and like waves. We would expect them to behave like particles. The movement of particles at this size is very random, and this is the Heisenberg uncertainty principle you may have heard about. It's physically impossible to know both the position and the speed of a particle at the same time. The more you know about one, the less you know about the other. And I've mentioned this already, the atomic world or the subatomic world is nothing like the world we live in. One of my favorite quotes by Niels Bohr, anyone who is not shocked by quantum theory has not understood it. So in class we did what I call the tiny teacup activity. If you fill a large teacup with water and you turn it over upside down, the water is going to come out. But I have these tiny, tiny little teacups that can fit basically a drop of water, and when you turn it upside down, the water does not come out. So why is that? Well, forces that win at the macro scale aren't as important at the nanoscale. So in a normal sized teacup, gravity pulls the water down and out of the cup. But in the tiny teacup, gravity doesn't matter as much because the drop's so small that other properties win, like water's special properties of adhesion, cohesion, polarity, and surface tension. They, quote-unquote, defeat gravity in this mini version. We did another activity. We threw a large styrofoam ball and it threw to the back of the room. And then you throw a tiny piece of styrofoam and you look completely ridiculous because it barely travels like 6 inches. Why is that? Well, there are competing forces, just like with the tiny teacup. When you throw a ball, though, it's a little different. There are drag forces that are proportional to the surface area, and there's inertia, which is proportional to the overall volume that resist changes in velocity. So how quickly an object slows down is given by this ratio of drag force to inertia. Drag force over inertia is equal to deceleration. There's a coefficient, which I call C, that depends on the fluid the object is moving through. So in this case it's air, and it's the same for both styrofoam balls, so that's not changing. And we're also assuming that the initial velocity, the speed at which you threw it, would stay the same for both throws, and the density of the styrofoam is the same. So the only things that are different are the surface area and the volume. So as something gets smaller, there's greater surface area for volume. So that means deceleration will be much greater. The drag force dominates over the inertia. There's 4 main important changes at the nanoscale. Gravity becomes negligible and other forces dominate, such as electromagnetic forces, positive and negative charges. Quantum mechanics is used to describe motion rather than classical mechanics. Again, this is the physics that we use at the microscale. There is a huge increase in surface area to volume ratios as particles become smaller. And this random molecular motion becomes more important. Little background with the original physics. This was largely developed by Isaac Newton in the late 1600s. This is the famous, the apple falls from the tree, and he is the first person to define gravity. You'll have heard things like, for every action there's an equal and opposite reaction. These are still relevant to our world today. What's interesting is they don't explain the observations that occur with atoms, molecules, and subatomic particles. So, the first problem that scientists ran into came about in the late 1800s. They were unable to use classical physics to explain blackbody radiation. So this is the radiation that is emitted by anything that's heated. So there was a scientist named Max Planck, and he was able to explain blackbody radiation with his famous equation, E equals h times F. E is for energy. And basically what you need to know about this equation is that it showed that energy comes in discrete packets, which he named quanta. Before this, physicists believed that energy could be discharged in any amount and that it was continuous. So quantum mechanics was born. It was able to explain new phenomena. It was based on probability and statistics, and it has a lot of terms, components. The electromagnetic waves, photoelectric effect, atomic orbitals, wave-particle duality, the uncertainty principle. These are all components of quantum mechanics. So let's talk about some of these. So electromagnetic radiation is really talking about the different types of waves. And I'll go back here for a second. You've probably heard the speed of light defined as 3 times 10 to the 8th meters per second. And if I put that into miles per hour, it's 670 million miles per hour. When you're talking about waves, there are two terms. There's the frequency, that's how many cycles per second, and the wavelength. So I have that defined in the picture below. That's crest to crest or trough to trough, the distance between two equal spots on a wave. And the speed of light is equal to the frequency times the wavelength. Here are the different types of waves. There's radio waves, microwaves, infrared, which is also known as heat waves. There's the visible waves, which unfortunately for humans, we can only see these, red through violet. There's ultraviolet waves, X-rays, and gamma rays. Imagine if our eye could detect all of these waves, how many different things that we would see. So a little review, which has more energy, red wavelength light or blue wavelength light? The answer is blue. It has a higher frequency. There are more crests traveling by per second, and it has a shorter wavelength. Let's talk about the photoelectric effect. This was something that Einstein worked on, and he realized if you shined light at a metal, an electron will basically be able to move. It'll come loose, it'll jump. If you shine a lot of this high frequency light, many electrons can move and be released from the metal. So on the other hand, if you shine light at a metal that doesn't have as high of a frequency like red light, no matter how much, no matter how intense that light is, electrons will not move. So there is a minimum frequency required for current to flow. It's not based on intensity. It's based on having this minimum frequency. And current flows when light hits. The number of electrons that are emitted depends on the intensity, if you have reached that minimum frequency. Okay, and here we're talking about photons, which are packets of light energy. Okay, so what are the applications? So because of the photoelectric effect, cameras work, night vision works, solar cells work. And by the way, what are electrons again? So electrons are parts of atoms. They're in a cloud around the nucleus. Every electron is associated with a specific energy, depending on what shell the electron, quote unquote, lives on. There's always some uncertainty. And then orbitals are these volumes of space where electrons are most likely to be found. Every orbital can hold a max of 2 electrons. Electrons can be in different energy states. The lowest is called the ground state, and that's closest to the nucleus. The excited states are the higher energy orbitals. So when a photon is emitted from an atom, basically what's happened here is an electron has gone from a higher energy state to a lower energy state. It can also happen in the reverse direction. If an electron gains energy, it can jump to a higher energy state. So you've seen this before in chemistry class. When you put a metal ion in a flame, such as sodium or potassium, electrons will get excited and they'll jump up to a greater energy level. And what goes up must come down. When they come back down to a lower energy, they release that difference in energy as light. So we'll see maybe for sodium a bright orange flame, for potassium we see a violet flame, for copper we see a green flame. So that amount of energy lost is equal to the energy of the light that's emitted. The double slit experiment is something that scientists still are fascinated by and they can't explain. So let's take a look at this. If you have two slits, like in the bottom left of this picture, and you pass waves through them, they will form a pattern on the back of the wall where there's a detection screen that basically shows areas of constructive interference and areas of destructive interference. So you will see there's on this screen 6 little bands here where these waves were interfering, these black areas. If you pass particles through a double slit, this is arranged a little differently, but here they are, you'll see two areas where the particles are hitting. So what about electrons? There's a video here, but just to explain what happens, you would expect the electrons to behave as particles, and you would see two spots on that detection screen. But what happens is you actually see the wave pattern. So electrons are behaving as waves. Okay, well, when you try to detect it and watch how they do that, because even if you put one electron through, it still forms the wave pattern, which means the electron must have gone through both places at once. So scientists are still really confused about this and how things happen, because it appears in the quantum world that things can be in two places at once. There's also the Heisenberg uncertainty principle. It's impossible to know both the location and the speed of a particle at the same time. So the more accurately you know one, the less accurately you know the other. We can be certain about large particles like a baseball, but in the quantum world it's completely different. So just as an overview, things we talked about, electrons and atoms are found in orbitals. Every orbital has an energy level. The closest energy level to the nucleus is the ground state. The higher levels are the excited states. Electrons can act as particles or waves, just like in the double slit experiment. Radiation can act like energy or waves. Atoms emit or absorb photons when their electrons change energy levels. And the uncertainty principle states that the more you know about an object's position, the less you know about its momentum. The laws of physics that are most important to a particular system depend on the size of that system. Are you talking macro scale or micro scale? At the nanoscale, almost all interactions are mediated by surface effects, so forces between objects are often proportional to their surface area. This is why surface-related forces that bond molecules and nano-objects together, like chemical and intermolecular bonds, are so much more important than gravity. The surface area to volume ratio is dramatically higher, up to 1 billion times higher for nano-objects than for human-scale objects. So surface-related effects dominate in our nano world.